Okay, you might or might not be familiar with partial derivatives. This is a symbol for partial derivative with respect to x of xy. Now, a partial derivative with respect to x means just the rate of change of the quantity xy with respect to x. So you take the change in xy due to a change in x, and you divide the change in xy by the change in x, and you get the rate of change of xy with respect to x. Just a very standard, simple rate of change. Don't expect you to understand all the subtleties of this. If you're taking multivariable calculus with this course, which isn't necessary, you'll get a much deeper understanding of what a partial derivative means. But for present purposes, I'm just going to tell you how to calculate a partial derivative, and I'm going to tell you what it means, and you don't have to worry about all the intricacies of the entire concept. Okay, so to calculate the partial derivative of xy with respect to x, we simply take the derivative treating x as x, treating y as if it was a constant. So if y is a constant, then the derivative of xy with respect to x, well, the derivative of x is just 1. You have the constant rule, so the derivative of xy is just going to be y times the derivative of x, which is just y. Okay, so what we can say then from this is that the change in xy due to a change delta x in the value of x is going to approximately be equal to the rate of change, y, multiplied by the change in x. And if you understand the concept of rate of change, which is the concept we began this course with, you should be able to digest this statement fairly easily. Just you multiply the rate of change, which is the derivative, which is y in this case, by the change in x, and that's going to give you the change in your original quantity xy. Similarly, in a little more concise notation, the partial derivative with respect to y of xy equals x, because again, we take the derivative with respect to y. That means we treat y as the variable. The derivative of y with respect to y is 1. X is treated as a constant, so that we just get x times 1, which is x. So that the change in xy due to the change delta y is about equal to x times delta y, the rate of change multiplied by the change in y. Now, all this is going to make more sense to you if you did a good job of covering differentials in first year calculus, if you did well with differentials, and if your course covered differentials to a pretty good level. Because all we're doing here is a differential. This motivates the differential. The differential of xy is going to be, well, the meaning of the differential would be the change in xy due to changes dx and dy, a change dx in x, a change dy in y. And we're simply going to apply something very much like a product rule. It is a product rule. The differential of xy, we have two variables, x and y. So what we do is we first take the partial derivative with respect to x and multiply that by dx, just much like the partial derivative here with respect to x multiplied by delta x. And then we take the partial derivative of xy with respect to y, which is x, and we multiply that by the change in y, analogous to this term. So that what we have is the change in xy due to a change in x plus the change in xy due to a change in y. So, assuming that dx and dy are small, that the change in x and the change in y are small, and let me digress, you're probably wondering why I'm using a delta x and a delta y here, and a dx and a dy here. Again, if you've done differentials, you're aware of that slight inconsistency in notation, but I'm not going to go into an explanation. You can just assume that a dx and a delta x mean the same thing for the purpose of what we're talking about right now. Okay, so if we divide the change in xy, because this is going to represent the change in xy. If we divide the change in xy by the value of xy, well, we get the change in xy as a proportion of the change of the value of xy. And if we multiply that result by 100%, we get the percent change in xy as a percent of xy. So we get the change. We can think of this kind of as a percent change. We haven't really done the percent. We haven't multiplied it by 100 to get the percent. But this is a change in xy as a proportion of xy. To get the change in xy as a percent of xy, we'd multiply it by 100%. Now, this change in xy divided by xy is obviously very easy to simplify. We just distribute the multiplication by 1 over xy. The y divides the y here, so we get dx over x. Over here, the x divides the x, we get dy over y. And we now see that the change, well, this expression is the change in x as a proportion of x plus the change in y as a proportion of y. Now, where does that get us? Well, if we were to multiply dx over x by 100%, we would have the change in x as a percent of x. And same thing with y. We could get the change in y as a percent of y. So that we can translate this to the statement we have here. If dx is the uncertainty in x and dy is the uncertainty in y, then the percent uncertainty in xy, which is this times 100%, is equal to the percent uncertainty in x, which would be this times 100%, plus the percent uncertainty in y, which would be this times 100%. What does this mean? Well, this means that the percent uncertainty in the product of two quantities is the sum of the uncertainties in those quantities. Now, that's a rule you're given in the first chapter of your text. And I actually don't remember how deeply the text goes into explaining that rule. We're officially kind of using multivariable calculus here, but I'm kind of waving my hands and referring back to what I hope you understand about differentials to give you a sense of where these rules come from, and also a tool, if you understand it well, for figuring out rules for combinations of quantities that aren't covered by the rules you're given in Chapter 1.